acid-base properties of ions and salts. So some ions can act as bases. These are the conjugate bases of weak acids. So we have hydrogen carbonate ion. This is the conjugate base of carbonic acid. Right? So if this base, hydrogen carbonate ion, accepts a hydrogen ion from water, it regenerates the weak acid, carbonic acid. Now, if we look at, talk about a solution of hydrogen carbonate, there has to be another ion present in the solution, right? You can't have a solution of just negative ions. So the other ion is called a counter ion because it counters the charge, right? So this is coming from a salt. It could be sodium hydrogen carbonate, also known as baking soda, sodium bicarbonate. So this is a soluble ionic compound, and when it dissolves, it forms two ions, sodium ion and hydrogen carbonate ion. This hydrogen carbonate ion can take a hydrogen ion from water and act as a base. So when we put this in water, we're going to have a basic solution, even though we're not putting anything with ammonia or any metal hydroxides in the solution. But this ion is the conjugate base of a weak acid, and so it acts as a base. Any questions? Well, I guess one more thing I want to say about that. Does the sodium ion here, if that was potassium or some other cation, would that matter to all of this? No. This is a spectator ion, and that's why it's often just left off, which, is distressing to a lot of students because they're like, but it says here sodium hydrogen carbonate, now you're just talking about hydrogen carbonate. Well, it's because the sodium's just hanging out. It's not actually doing anything, but it is there. So we can think of any anion as being the conjugate base of an acid. So we've used HA to stand in for generic acid, right? HA. When that acts as an acid, let's write it out here. So when that acts as an acid, it loses a hydrogen ion and forms A-, right? This is the conjugate base of this acid, this anion. So any anion we can think of as the conjugate base of an acid. So we can look at nitrate ion. And if that acts as a base, it's going to take a hydrogen ion and it's going to form HNO3. Everybody cool with that? So we can think of any anion as a conjugate base, but not every anion acts as a base because it depends on the strength of the acid. So here, when nitrate acts as a base, it becomes nitric acid. What kind of an acid is nitric acid? It's a strong acid, right? So we learned that nitric acid is a strong acid. So when you put that into water, it ionizes completely. There's no equilibrium here. It ionizes completely. So if I have nitrate ions, are they going to react with hydrogen and reform this? No. No, they're not. So here we have a strong acid. Its conjugate base doesn't act as a base. We say it's pH neutral. So the conjugate base of a strong acid is pH neutral. If we have something like, nope, I don't want that. I don't know, acetic acid. Acetic acid is a weak acid, and so it ionizes partially, forming hydrogen ions and acetate ions. this is in equilibrium. There are significant amounts of both reactants and products. So if I have a solution of acetate ion, will that accept hydrogen ions and reform acetate? Acetic acid? Yeah, it will, because this is a weak acid. So the acetate ion can act as a base. So the conjugate base of a weak acid is a weak base. The conjugate base of a strong acid is just neutral, nothing. The weaker the acid, the stronger the conjugate base. So chloride ion. Chloride ion is a conjugate base of HCl, which is a strong acid. So chloride ions do not affect the pH of the solution at all. The fluoride ion acts as a base. It makes the solution basic because it's the conjugate base of a weak acid. So HF is a weak acid. So when it reacts, gets dissolved with water, it forms hydronium ion and fluoride ion. And if we have just fluoride, if we just add fluoride ion, could we just add fluoride ion? Do you have a solution of just fluoride ions? There'd have to be a counter ion, right? So there could be like sodium fluoride. If you had aqueous sodium fluoride, that's sodium ions plus fluoride ions. Right? Because this is a soluble compound and so it dissolves. And these fluoride ions then can react with water. Fluoride ion with a water molecule So the fluoride ion can take the hydrogen ion from the water, forming HF. Yes?
But it doesn't ionize completely because it's not a strong acid.
Right. This is a weak acid. And so the relationship between the weak acid and its conjugate base is an equilibrium. With HCl, I mean, you could write a similar thing and say, well, why doesn't this happen? Why can't we write this? Because this is a strong acid. And in solution, there are no HCl molecules because it all goes the other way. It ionizes completely. And so chloride doesn't act as a base. Fluoride acts as a base because it takes a hydrogen ion, it becomes HF. So what we have here between the acids and the bases is we've just got this hydrogen ion being passed around. And whether it's a strong acid or a strong base, weak acid or a weak base, depends on how tightly does it hold on to that hydrogen ion. And when I think of holding tightly to a hydrogen ion, I think of something that's strong, right? And it's actually one of those opposite things. This is a strong acid because it will dissociate completely. So I told you I think about these hydrogen ions as being babies, and then the chloride ion is probably the mom because she's an anion and the nonmetals are non-masculine. So that's the mom, right? So if this is a strong, confident mom, she's willing to hand her baby to a babysitter and go and do stuff for herself, right? And if she's a weak, insecure mom, like fluoride, she's going to hold on to that baby and not going to let anybody else take care of it. I know, weird, huh? Does that make any sense? So HF is present in solution. And anytime there's water present with fluoride, you're going to make some HF. And in order to make HF, you're going to produce hydroxide ions. And there's going to be an equilibrium there. So here we have a list of acids and their conjugate bases. in order of strength. So over here on the left side we have acid strength, and up at the top we have the strong acids. There's HCl, the sulfuric acid, nitric acid. Hydronium ion is considered a strong acid. And then we get into the weaker acids, and then we get down here to things that just are really negligible. They don't really act like an acid at all. On the other side of the black line in the center here, we have the conjugate base of HCl. These strong acids ionize completely, and so this base is going to be so weak that it's not a base. It's going to be neutral. And this HSO4 and the nitrate, these are conjugate bases of strong acids. The conjugate base of H3O plus is water. Water does act as an acid and as a base, but both of them are weak. And then as we go down here, the acids are getting weaker and weaker, but the conjugate bases are getting stronger and stronger. So it's a trade-off. We get down here, hydroxide ion is what we get from strong bases, sodium hydroxide, lithium hydroxide, etc. And then we've got sulfide and oxide are also, oxide. Those are also strong bases. Any questions? Okay, so we need to be able to identify whether an anion is basic or pH neutral. So here we've got this anion, CHO2 minus. And you probably don't know the name of that, and that's fine. You don't need to know the name of it. That's an anion. It can act as a base. When this acts as a base, what do we get? Well, we'll put the H on at the beginning. HCHO2. And it's going to take 1 because it has a -1 charge. And then we'll get hydroxide ion. The relationship between a base and its conjugate acid, or acid and its conjugate base, is 1 hydrogen ion. So here I'm going to add H plus to this, and I get HCHO2. Now, that's an acid. Is it weak or strong? It's weak because it's not one of the 6, right? Anything that's not one of the 6 strong acids is a weak acid. So is this a weak base? Yes, it is. It's the conjugate base of a weak acid. This is a weak base because this is an equilibrium. So this one is a weak base because it's the conjugate base of a weak acid.
I thought you said the weaker the acid, the stronger the conjugate base.
That's true. The weaker the acid, the stronger the conjugate base, but it is a weak acid, and so it's a weak base. Here we're not saying, is it a really strong weak base or a very weak base? We're just saying, is it a base? Yes, it is. Okay, here's perchlorate ion. So when I add a hydrogen onto that, what do I get? I get HClO4. So, I mean, you can do this. You can also just say, well, what if I add an H plus to that? What do I get? HClO4. Ask yourself, what kind of an acid is that? That's a strong acid. So is its conjugate base, does it act as a base? Mm-mm. This does not act as a base. So this one's pH neutral. You probably haven't thought about all these different solutions that we've used in lab, and I wouldn't expect you to think about them. When we've got a solution where, say, we need the sodium ion for something, we need to be careful what counter ion we put with that so that we don't change the pH of the solution. And so things like perchlorate ion are good, chloride ion, iodide, bromide, those are good because they're pH neutral. So we can determine the pH of a solution with an anion that acts as a base. But we need to know what Kb is. So the conjugate base of a weak acid, you can look up the acid ionization constant for the weak acid. If you look hard enough, you can also find Kb, but there's actually a very simple relationship between Ka and Kb. So here we have HA, the acid, right? So we can write an equilibrium expression. So that's going to be H3O plus times A minus divided by HA, right? And over here we have the anion acting as a base. And so we could write the base ionization constant for that, be hydroxide ion times the weak acid divided by A minus. Let's see what happens if I multiply these. Ka times Kb. So at H3O plus and A minus over HA times OH minus times HA over A minus. So we've got some terms that are going to cancel out, right? We've got A minus on the top and the bottom. We've got HA on the top and the bottom. And we're left with H3O plus times OH minus. And what does that equal? One times 10 to the minus 14, which we also call Kw, the ionization constant for water. So the relationship here is that Ka times Kb is equal to Kw. So if you know Ka, you can find Kb. Any questions? So let's find the pH of a 0.250 molar sodium acetate solution. No, I didn't give myself the Ka. Hey Siri, what's Ka for acetic acid?
I found something on the web about what's Ka for acetic acid. Check it out.
Thank you, I will. So, Siri, oh, don't do that to me. Yeah, I wasn't done. Hey Siri, what's Ka for acetic acid?
Okay, I found something on the web for what's Ka.
Okay, so there's Ka. We looked it up. It wasn't given to us. Now, on an exam, you would either be given the Ka, the Kb in the problem, or you'd have a table where you could look it up. You don't memorize these things. The one thing you memorize is Kw, 1 times 10 to the minus 14. Okay? So we're supposed to find the pH of this solution. So let's look at the dissociation or the association of this and figure out what's going to happen here. So, is this an acid? Does it start with H? No, it doesn't. This is sodium acetate. That's an ionic compound that's soluble. So what ions does it form? Sodium ions and acetate ions. And so here's the anion, and what we're going to look at is, can that act as a base? So if I have C2H3O2 and I have this acting as a base, and we'll do it this way. It's going to accept a hydrogen ion from water and form hydroxide ion, right? It's acting as a base. This is acetic acid. This is a weak acid. I looked up its acid ionization constant. So what I've got here is the ionization equation for the base, right? So if I'm looking at an equilibrium constant that's equal to C2H3O2 times hydroxide ion over acetate ion, is that Ka? No, it's Kb. I have Ka. So I need to find out what Kb is. So Kb is equal to Kw divided by Ka. Make sure that you're using scientific notation correctly in your calculator. So 5.5 repeating times 10 minus 10. So that's what Kb is. Any questions? If Ka is big, Kb is small. If Ka is small, Kb is big. So now I can go over here. This 0.250 molar sodium acetate. The sodium ion is there, but it's not going to do anything. It's just the counter ion. It's a spectator ion, so we're not going to worry about it. We're just going to let it come off of the acetate and say, well, then I've got 0.250 molar sodium ions, which I don't care about, and 0.250 molar acetate ions. And those acetate ions are going to react with water and form acetic acid and hydroxide ion. But initially there's no acetic acid and there's essentially no hydroxide ion. So I'm doing my ice table here. This is going to go down by x, this is going to go up by x, and this is going to go up by x. At equilibrium, I've got 0.250 minus x, x, and x. So my Kb, 5.556 times 10 to the minus 10 is equal to x squared over 0.250 minus x. Anybody else get that? 1.1785 times 10 minus 5. It's my hydroxide ion concentration. But we want the pH. So we're going to find the pOH. Here's a calculator shortcut. If you just do the log of 1.1785 times 10 to the minus 5, it'll give it to you as a negative number, and then you can just add it to 14. pOH is 4.9286. pH then is 14 minus that. .07. Any questions? Yes?
How do you know that gave you hydroxide concentration?
Because that's what X is.
Oh, okay.
Yeah. That's a good question. So we find X, and then it's very important to recognize, well, what does X mean? Because in this situation, X was a thing that I needed, but in other situations, if this had a starting value, if it wasn't 0 to start with, and I had a change of X, I'd have some number plus X that I'd have to be doing a calculation with. Like if I wanted to know what the acetate concentration was, I'd need to take 0.25 and subtract X from it. Any questions? Other questions? So anions can be weak bases. Cations can be weak acids. So there's 3 categories of cations. Cations that are counter ions of strong bases. So these are pH neutral. Anions that were counter ions of strong acids. Well, never mind. So strong bases. This is going to be things like calcium, sodium, potassium. Come on. Okay. So calcium ion, if we put hydroxides with that, we get calcium hydroxide. And we should recognize that as a strong base. Computer's being weird here. It's got a little box in the middle there that's blank. So sodium, potassium. This is not going to act as an acid because this reaction actually doesn't go in this direction at all, right? Calcium hydroxide dissociates completely and forms calcium ions and hydroxide ions. So these sorts of cations aren't going to do anything. They're pH neutral. We can get cations from non-ionic weak bases, such as ammonia. So if we have a weak base and we add a proton to its formula, we get a cation. That cation is the conjugate acid of the weak base, and so it is also a weak acid. So when we have a solution containing the conjugate acid of a weak base, we can calculate the pH using Ka, which we derive from Kb. Isn't this fun? Another group are small, highly charged metals. Highly charged metals, such as Al3 plus and Fe3 plus. These will form weakly acidic solutions, and this is kind of a strange one. So aluminum can complex with water molecules and form a complex ion. We'll talk more about those later. That complex ion can take a hydroxide ion from water and is taking one of these waters and the hydrogen ion from this one, and back that up. It's donating a hydrogen ion to this water molecule, and so we end up with this even stranger complex ion. I don't expect you to really understand what's going on here, but just memorize that Al3 plus and Fe3 plus act as weak acids. So we're going to identify each of these as either a weak acid or pH neutral. So lithium ion. pH neutral, because that is the conjugate acid of its strong base. So this is pH neutral. And if you look at this and you say, well, how could I react that with water to form hydronium ion? You're like, it's kind of hard to figure out. Here we've got CH3 NH3 plus. So this has hydrogens on it. It could conceivably donate a hydrogen to a water molecule and form CH3 NH2 and hydronium ion. The lithium can't do that. Lithium has no hydrogen on it, right? But this one has hydrogens and a positive charge. This is very much like NH4 plus, and this is very much like NH3. This is one of those weak bases. So, is this ion a weak acid or pH neutral? It's a weak acid. And then there's Fe3 plus. It's a weak acid. Why? Because I told you so. That's good enough. What's the other one? Al3 plus. So Al3 plus and Fe3 plus, they're small, they have high charges, and they do funky things with water, and they act as acids. We'll call that good for now. Okay, so we looked at anions and we looked at cations separately, and then we're going to look at them together